Okay, Cram's rule means if a carbonyl compound is attached to a chiral compound, okay, optically active compound, then it is possible to get erythro and trio compounds. But as per the Cram's rule, it is possible to predict the major product. Okay, so that is called Cram's rule. So for that, I am taking the mechanistic pathway. 1 minute. Okay, so for that, I am taking mechanistic pathway. The mechanistic pathway is this is a carbonyl compound. So more particularly, what I am doing here, I am taking the carbonyl compound which is attached to a optically active in Sahar's projection formula. So this is Sahar's projection formula. So this is not, this can be converted into Newman's projection formula. How we can convert? So this will be the front carbon and this will be the back carbon. And you have to view from this side. So when you are viewing from this side, so it will show that the D should be is on the left hand side. When you are viewing from here, okay. Yes. So when you are viewing from here, ethyl group is on the left hand side, D is on the right hand side. And we know that a nucleophile should attack from the less hindered side. So this part is the less hindered side, whereas the ethyl group is the bulky one. So what will happen if it is attacking from this side? OH will go this side and CH3 is coming over. That's what I have written here. Then afterwards, here there will be a movement. So CH3, in this, CH3 is moving in a clockwise direction and coming over here. If CH3 is moving in a clockwise direction and coming over here, OH will come over here. Okay, and then from here to here, again, the phenyl group, second back carbon atom, it is moving in a clockwise direction. So that means when phenyl is coming over here, D will come to this, ethyl group will come to this. That's what I have written here. So from Newman projection formula to the Fischer projection formula, how you can write? So what is that? The front carbon, CH3 is this, OH is this, and H is this. And the back carbon atom, phenyl is down, D is on the left hand side, and ethyl group is on the right hand side. So here, what you need to remember, you should just look into the both the groups. So this one is ethyl, this one is deuterium. So ethyl takes a priority and it is on the right hand side. So you just look into these two groups. One is hydroxy, another one is H. Hydroxy group is on the left hand side. What it means, a priority group hydroxy and then ethyl groups are in opposite place. So that is the reason. So this one is called trio. So this is how you can predict the predominant product, and the predominant product is trio in the case of a nucleophile is attacking a carbonyl compound which is attached to a optically active compound. So with this, I will take one more example. Okay, so I will go to the next slide. Right, now it will move. Okay, so this is one more. So here also, when you should look it from this side. When you are looking from here, the deuterium is on the right hand side. So that is the reason this is right hand side. And the CH3 is on the left hand side. So this is how you convert a Sahar's projection formula into the Newman projection formula. Once you are converted into Newman projection formula, then a nucleophile is attacking. Where it will attack? It will attack from the less hindered side. If it is attacking from this side, what will happen? The hydroxy group is going to this wards. So that's what I have written here. So from here to here, there will be a movement. Okay. So the ethyl group is in a clockwise direction. It is coming over here. So this is the eclipsed one. This will be the staggered one. And afterwards, what will happen? Back carbon also, the phenyl group will go in a clockwise direction and going over here. So that's what I have written here. So from this eclipsed form is converted into a Fischer projection formula. So how you are converting? You have to write the front carbon, that is ethyl hydroxy here, left hand side, CH3 is on the right hand side. Once you return front carbon, go for a back carbon, the phenyl group, you have to write it on the down. The left hand side D is there, that you write. Right hand side CH3 is there, that you write. Once after writing, you can observe that between these two groups, this takes a priority. Similarly, between these two groups, this takes a priority. And the priority ones are in opposite place. That is the reason this is 3O. This will be the major product, and it is explained through Prelog's method. So by this Cram's method, one should able to identify or what is called mention that trio will be the major product. So now what I will do, I will go for a next slide. So next slide is about the Prelog's rule. So in this Prelog's rule, it's a correlation method. So it is correlated. How it is correlated? It is correlated configuration of chiral alcohol with those of alpha hydroxy acids, for example, mandelic acid and atrolactic acid. So here what is happened? Phenyl glyoxylic acid is esterified with an optically active alcohol called menthol. Menthol is a optically active compound. Phenyl glyoxylic acid is it's a keto acid. So further, after the esterification, it was treated with Grignard reaction. Once there is a treatment of Grignard reaction to the ester, keto ester, so there will be a configurational changes. Then this on hydrolysis, it will give you a hydroxy with that of the alcohol. So I will show you that in schematic representation. This is menthol, and this one is glyoxylic acid. It's nothing but a keto acid. So when these two are treated, when these two are react, so there will be a esterification formation. The ester is this, and the Grignard reagent, it will attack this carbon. It won't attack ester carbonyl carbon, but it will attack ketonic carbonyl group and forming a compound like this. Then afterwards, what will happen? It will hydrolysis. Ester is hydrolyzed. You can find that this is also optically active, this is also optically active, whereas this one is optically inactive. So this is how Prelog's correlated the structures of glyoxylic acid with the menthol. Okay, this is about the Prelog's rule. So there are questions on Prelog's rule as well as the Cram's rule. So with this, your syllabus is completed. So what you know, maybe what I will do now onwards, I will go for a question answer discussion. And what you have to do, you have to prepare for one test. So that test comprising the 3 chapters. Otherwise, what I can say, 2 units. So 2 units means heterocyclic chemistry, carbohydrate chemistry, and then stereochemistry. All these things are included. So you should be ready with ready for this internal test. Maybe you can take in the next week or so. Maybe I will inform a date. Otherwise, you can also suggest the date. So up to that, what I will do, I will discuss the question answer. What is that? Question answers asked in the university exams. Okay. So now I will take up the question answers on stereochemistry. So what is Prelog's rule? Just now we discussed. No, this is a correlation method. It is what will happen here. A optically active methanol is menthol, not the methanol. Menthol and methanol is different. Methanol is CH3OH. Methanol is a terpenoid. Okay, naturally occurring, and it is also having a optically active chiral center. So a keto acid, when it is treated with optically active menthol, it's converted into a ketoester. The ketoester, when it is treated with Grignard reagent and followed by hydrolysis, gives two chiral compounds. Here, Prelog is correlated the glycolic acid with the menthol. That's what you can mention about the Prelog's rule. And explain the conformational analysis of cyclopentane. Cyclopentane means a 5-membered ring. So a planar moiety you can write. Another one is the what you call envelope form. So, and you have to mention that envelope form will be the more stable compared to the planar one. That's what you have to explain. And the prochirality. Prochirality means here you have to give a definition. Definition how you can give the compound. So the one which can be converted into a optically active or chiral compound in a single transformation. Say for example, a carbonyl compound can be converted into a optically active. Okay. So more particularly, the carbonyl compound which is attached to a two different substituent. So that is only possible to convert into a chiral compound in single step. When it is treated with Grignard reagent or maybe a hydrogen cyanide, it is possible to convert. And also you should aware that carbonyl compound, it is having a two phase. So one is re phase, another one is C phase. Those things also you should be able to identify. So you can mention those also when you are writing the answer for this. Explain means you have to little elaborate to get a 3 marks or 4 marks or 5 marks. Then anyway, here itself is there, no? So okay, what is the question? Whether the following compounds are optically active or not. So justify. It's a 4 marks question. You can observe that. So this is a carbonyl compound. So since this is not a optically active, but this is a prochiral molecule. But this can be converted to a optically active in single step. And here what is the phase is there. So you can observe that this is the one priority and this will be the second priority. So when you are moving in a anti-clockwise direction, that means it's a C phase. It is having a C phase. Now nucleophile can attack and leads to a chiral compound. Of course, this one is a optically active compound, but you have to explain whether this is a R configuration or S configuration. How you can form? So you need to convert this into a convenient form. How convenient form? So these two groups are away from the observer and these two groups are towards the observer. So you can observe that when you are assigning a priority means the hydrogen should occupy this position. So up to that you have to keep this as a constant, and these three you have to move it in a clockwise direction until getting this group here. So once, so that means what it means. So this can go over here, this can come over here. One rotation. Then afterwards, second rotation, Br will come over here, and then no. Yes. Okay, Br will come over here, and then CH3 will come over here, and H will come over here. So that means if you are comparing the priority wise Br and chlorine, Br is having higher molecular weight. That is the reason bromine. When bromine is coming over here, that will be the first priority. This will be the second priority, and this CH3 will be the third priority. That means it is moving in a clockwise direction. So that is the reason this configuration is having R configuration. So, and then assign R and S configuration for the following. So you have to write the structure of glyceraldehyde. What is glyceraldehyde? CHOH. Okay, and then first you can write CHO. Okay, maybe I will take a pencil. Okay, CHO. Here CH2OH. Okay, and this one is H. So this is a glyceraldehyde. Okay, after writing a glyceraldehyde, you have to assign the R and S configuration to the glyceraldehyde. Then afterwards, you have to write the serine. Serine means, so what is the difference between the serine and glyceraldehyde? So I will take a pointer. Okay. So what is the difference between the serine and glyceraldehyde? Serine is a amino acid. More particularly, here there will be a NH2 group, and here there will be a COOH group. That's all. So the difference between the glyceraldehyde and serine means NH2 should be here, COOH should be here. That's all. That is the serine. But he is asking about the L-serine. L-serine means the NH2 should be on the left hand side. So left hand side NH2, H is here, COOH here, that is called serine. So once you write serine, you have to assign, that's all. You have to, then after writing the serine, L-serine, you have to assign the R and S configuration to that L-serine. That's all. So you have to write the glyceraldehyde, that means this one. Then afterwards, you have to assign the R and S configuration to this. So when you are assigning R and S configuration, same rule, you convert this into a straight chain one, and these two groups are towards the observer, these two groups are away from the observer. Since the towards the observer one H is occupying, that is the reason these three groups you should rotate in such a way that the hydrogen should come over here. It requires two rotation. Then after the rotation, what you will get? You will get OH over here, CH2 over here. So then OH is the first priority. This will be the second priority. That means D-glyceraldehyde showing the R configuration. So then L-serine, what you need to do? L-serine means NH2 is here. Okay. And then H is here, CH2OH. Then H is here. So that means since H is towards the observer, it requires one rotation. Keep this as a standard and rotate it. What will happen? H will come over here, CH2OH will come over here, NH2 will come over. So that means NH2 takes the first priority, and this will be the second, this will be the three. That means L-serine showing a S configuration, D-glyceraldehyde showing a R configuration, that you have to mention by writing and mentioning the R and S. You will get a 4 marks question, 4 marks for that. Then afterwards, write the Fischer projection formula of 3-chloro-2-butanol. So here what you need to do, Fischer projection formula. So Fischer projection, okay, I will take a pencil. So when you are writing Fischer projection formula, so you can write like this. Okay, then what is the butanol? Is mentioning the butanol, 2-butanol. So that means at the second position there is a hydroxy group. So I will take this as a second position, and here I will mention the hydroxy group. Okay, and third position there is a chlorine. Okay, so here I will write a chlorine. Okay, then the remaining things are, one should be the CH3, this should be the CH3. Okay, this also CH3. Okay, and the remaining things are hydrogen. This is hydrogen. Okay, this also hydrogen. Okay, so what is the question? Write the Fischer projection formula. Trio is asking, but actually this one is a erythro. So trio you want means you can write that chlorine and hydroxy group are in opposite place. If the chlorine and hydroxy groups are in opposite group, that means chlorine as well as hydroxy group should be in the opposite. So OH here, Cl here, Cl here, OH here. So that structure is called the Fischer projection formula of trio. That's all. Okay, then after that you can also assign R and S configuration to that. Okay, then assign the R and S configuration to these two molecules. First you have to find out where is the chiral center. So this one is the chiral center. Similarly here this one will be the chiral center. After knowing the chiral center, you have to convert into a Fischer projection formula, and after finding out the Fischer projection formula, you should aware that the least priority should be in the down. And for that what you need to do, you have to keep the top group should be constant and the remaining thing should be on the clockwise rotation. So thereby you can find out which one is R, which one is S. Okay, it's a 2 marks question. So what you can if you are just looking into the this moiety, so what you can observe that, so these two groups, so these two groups are horizontal groups and these two groups are away from the observer. So that means what you can do, CHO is, it should be right on the top, CH means OCH3 twice is on the down, and left hand side C2H5, right hand side CH double bond CH2. So which one is the least priority group? So least priority group is C2H5, but whereas it is in the towards the observer, that is the reason we have to rotate it in a clockwise direction. So how that means what will happen? This will go to here, that will come over here, then afterwards it will come over. Okay, right. So then what will happen? So maybe let's take that pencil and write it so that we will have a clarity. So when you are writing this, so first you have to write the so away from means vertical groups, and here towards the observer one. So C2H5 is this, C2 H5, C2H5 is this, and this one is CH, double bond, CH2. Okay, and here CHO group. Okay, and here down CH, O, CH3. Twice. Okay, so this is how you are converting into a well, I will take a pointer now. Okay, so this is how you are converting into a Fischer projection formula. So then what will happen? This will be a constant, and this C2H5 will go over here. CHOH, CH double bond CH2 will come over here, and this CH OCH3 twice will come over here in the first rotation. Then after in the second rotation, what will happen? CH2 CH2 CH OCH3 will come over here. Okay, and then CH double bond CH2 will come to this position. Afterwards, what you need to do, you need to assign a priority. So when you are looking at priority, double bond is 1. Another thing is oxygen. Definitely oxygen will take a priority. So that is the reason this is 1, this will be the 2, this will be the 3. So what it means, S configuration is the this one. So similarly, this way you can also find out the configuration for this. How you can found, maybe again you have to convert this into a Fischer projection formula. So when you are converting this here, you can also observe that this group is different, this group is different. Overall, this chiral carbon atom attached to 4 different groups. Okay, then afterwards what you need to do, you have to convert into a what you call Fischer projection formula. So when you are converting it to a Fischer projection formula, this hydrogen indicates that it is towards the observer, and this group should be away from the means this is away from the observer, this group should be towards the observer, and this as well as this should be away from the observer. So what will happen, maybe what you can do, you can observe from here. Otherwise you just convert into a such a way that the hydrogen should attain a least priority. Then you assign the priority and then find out the R and S to this moiety. Otherwise, what I will do, I will try to do it now itself. Okay, so first you just look into the what. Okay, I will find that. Okay, so this how you can write hydrogen should be here. You can write hydrogen. Okay, and then CH2 I will write here, CH2 and then CO. That's what I will write. And the vertical groups CH2 I will write. Okay, and the down one, it should be CH, CH, and then Me twice, Me twice. Okay, so now you have to keep the CH2 as a, I will take a pointer. Okay, so you have to keep CH2, means this group should be constant and remaining thing you have to rotate. So until this H will come to down. So in the initial first rotation, this H is coming over here, and this CH2, this is CH2, CH3 twice will come over here. This will come to this position in the first rotation. In the second rotation, okay, then CH2 Me thrice is coming over here, and CHCO will come to here. So now at this stage, and H will come over here. At this stage, you have to assign the priority. So since CHCO is containing, so CHCO will come over here. So that takes the priority. That is the first one, and dimethyl 1 will be the second priority, and this will be the third priority. That means it is moving in a anti-clockwise direction. So that means this will be the S configuration. So that is how you can find out the R and S configuration. So it is asked for the 2 marks question in 2015. So with this, I will go to the next slide. So next slide is about explain the optical isomerism in allenes and spiranes. It's a direct question. You can write it allenes and spiranes. Maybe you can take 2 examples of allenes, 2 examples of spiranes you can take, and predict the R and S configuration for that. So you may get 4 marks. And give the account of conformational analysis of 1,3 and 1,4 cyclohexane diols. So here the substituents are hydroxy group, and the hydroxy groups are at in one compound 1 and 3 position, axial hydroxy group. In another cyclohexane, it is at 1,4. Okay, both the examples I have discussed. You have to write the most stable one and less stable one. You have to write it. Okay, then discuss the relationship between the optical activity and the elements of symmetry. So you can write that optical activity is an experimental phenomena, and this one will be the theoretical one. So when you are writing the elements of symmetry, you have to mention the plane of symmetry, center of axis of symmetry, improper axis of symmetry. When you are writing optical activity, so you have to say that what is plane polarized light. So what happens when plane polarized light is passed through a optically active compound, that you have to mention. And here again you need to assign R and S configuration to these 2 moieties. So both are, this is optically active, this also is optically active, but you have to find out which again this is a amino acid. So more particularly it's called alanine. Okay, and of course here the 2 chiral centers are there. Maybe you need to find out what is the configuration on this chiral, and also what is the configuration on this chiral. Okay, maybe in order to do that, what you need to do, of course this is fine. I think what you can do, directly assign, because no, you cannot assign, because hydroxy is towards the observer. You have to convert this into a convenient form. So when you are converting, these two groups are horizontal, these two groups are vertical one. And you have to rotate it until getting hydrogen in the down, then you assign the priority and then check it over. So similarly in this, when you are assigning the when you are taking into a convenient form, so this you can write it as a 1 carbon, and these two are away from the observer, and these two are towards